Okay, let's dive right into this. Welcome to today's Explainer, where we're going to unpack a pretty fascinating engineering showdown. When you're engineering the future of renewable energy, specifically wind power, you face this massive, absolutely crucial hurdle right at the starting line. How do you predict how well your design is actually going to perform? We really need efficient aerodynamic models to figure this out, especially during those early preliminary stages of design and parametric analysis. It's a total high-stakes balancing act between keeping computational costs down and getting real-world accuracy.
So how do we predict a wind turbine's power without building the whole thing first? You can't just go out and build a dozen full-scale turbines to see which one performs best, right? That would cost an absolute fortune. We have to model their performance mathematically beforehand, but on the flip side, running massive supercomputers to simulate every single microscopic gust of wind, that's not exactly practical or cheap either. We desperately need low computational cost models that still deliver reliable data. The big question is, which model do you actually trust?
So here's our game plan for today's Explainer. First, we'll look at the VAW modeling challenge. Next up, DMST versus LFVW. Then we'll dive into the performance data matchup and finally wrap things up with the LFVW advantage.
All right, Section 1, the VAWT Modeling Challenge. Today, we're zeroing in on VAWTs, vertical axis wind turbines. The source material specifically looks at how these models apply to a small-scale Darius H turbine. Because of their unique spinning geometry, predicting the aerodynamics here is incredibly complex, and that's exactly why having highly efficient models is absolutely mandatory during those preliminary design stages.
These simplified mathematical models essentially have to run a really rigorous physical obstacle course. It's way more than just wind hitting a blade. The models have to accurately account for induction losses, that drop in wind speed as it actually approaches the turbine. They have to map out wake expansion, which is how that turbulent air behaves after it's passed through. And of course, they have to factor in unsteady aerodynamic effects because the blades are constantly changing their angle relative to the wind. That is a ton of complex physics to cram into a low-cost computational model.
Okay, moving right along to Section 2, DMST versus LFVW.
Let's meet our two contenders. We have the DMST model, that's double multiple stream tube, and then we have the LLFW model, or lift line with free vortex trail. Both of these are widely used, simplified aerodynamic approaches. Engineers use them all the time to save computing power, but as we're going to see in a second, they definitely do not yield the same results when put under pressure.
So how do you actually figure out which one is better? Well, the researchers set up a real stress test. Step 1. They applied both models to that small-scale Darius High turbine. Step 2, they evaluated two modeling configurations with different levels of physical complexity, really testing how they handle stuff like wake expansion. And Step 3, the ultimate reality check, validating the model predictions against actual experimental data reported in the literature, basically holding the math up to physical reality. Let's see the results in Section 3, the performance data matchup.
Right out of the gate, the data reveals a pretty major flaw with our first contender. The DMST model tends to overestimate the maximum power coefficient. Think about that. If you're an engineer relying on this model, your simulation is basically telling you your turbine is going to generate more power than it physically ever could in the real world.
Let's unpack exactly where the DMST falls short, because the overestimation of the maximum power coefficient is really just the start. It also shifts the optimum operating point to a higher tip speed ratio. Now you might be thinking, well, we can just tweak the model, right? But the results show the DMST model still completely fails even when corrections for tip losses are incorporated, and even when variable induction factors are applied. The underlying model just misses the reality of the physics.
And this is absolutely critical. By shifting the optimum operating point toward higher tip speed ratio, or TSR values, the model is fundamentally telling you to run the turbine faster than you actually should to hit peak efficiency. In engineering, precision is quite literally everything. Having an inaccurate prediction of your optimal operating point could entirely tank the effectiveness of a wind turbine project.
So, how did the other guy do? Let's get into Section 4, the LFVW advantage.
When we switch over to the LFVW model, it's like night and day. It brilliantly succeeds exactly where the DMST stumbled. It accurately reproduces the complex wake dynamics. It accurately captures the non-stationary or unsteady aerodynamic effects. Because of that, it achieves much better agreement with the experimental data. And the best part? It's reliable across the entire operating range, not just at one specific speed.
So, comparing them head-to-head on the most vital metric, peak performance,
While the DMST overestimates power and totally shifts the peak TSR, the LFVW model accurately captures both the magnitude and the precise position of peak performance. It tells you exactly how much juice you'll get and exactly what speed you need to spin to get it.
Which brings us to the definitive conclusion from the source material. By accurately capturing that peak performance, the LFLVW is, and I quote, identifying itself as a more reliable model for the aerodynamic prediction of VAWTs. When you absolutely have to balance computational efficiency with accuracy and early design, the lift line with free vortex trail model is hands down the winner.
And that really wraps up our explainer for today. Using the correct, highly accurate models early on means we reduce errors, optimize performance, and really push the boundaries of renewable energy. It kind of leaves you wondering, with the LFVW model giving us these incredible predictions, just how much more efficient can our future vertical wind turbines truly become? Thanks for joining me today to explore this, and definitely keep questioning the science.